So this is the real meat of multivariable calculus. We're going to be talking about partial derivatives today. So the learning goals are to be able to compute partial derivatives, to be able to have a graphical interpretation of what a partial derivative represents. We're also going to estimate partial derivatives based on contour plots, and we're going to calculate higher order partial derivatives. So our first goal is to compute partial derivatives. Before we get to the computation, though, I want us to refresh our memory about what a derivative is in a single variable setting, because it's going to be directly analogous to what we're going to do in the multivariable setting. So way back in the day, you all remember this, you all love this. Let's say that I have a single variable function, let's call it f of x. And when we computed the derivative of f of x, our definition of derivative was given by a limit as h approaches 0 of f of x plus h minus f of x all divided by h. So in this case, if I wanted to evaluate the limit at some point a, instead of having x's, I would be looking at what is f prime of a? Well, it's equal to the limit as h approaches 0 of f of a plus h minus f of a all divided by h. Graphically, this derivative, if I have a here, let's say a plus h is some h distance over from a, and f of a is going to be whatever my output value is, and f of a plus h is whatever the output value of a plus h is. So if I'm looking at the derivative, it's going to be the difference in the functional values divided by this distance, or the slope. As my h values get closer and closer to 0, these slopes of these secant lines are getting closer and closer to the slope of the tangent line. Boring. Carolyn, you already know this, right? Well, I know. I hope so. It's okay. Instead, let's talk about what this means in terms of 2 dimensions, because our definition is going to be very, very, very similar. We're going to call our partial derivative with respect to x. And that's defined by, well, let's introduce some notation first. Our partial derivatives we write with curly d's instead of regular d's. I'm not sure where this convention came from, but this is to differentiate the fact that I'm taking a partial derivative, meaning that f is a function that has more than one variable. So this is one way that I write my partial derivative. Another notation for writing partial derivatives is to say f sub x. The subscript is telling me that I'm taking a partial derivative with respect to x. And if I'm going to evaluate this partial derivative with respect to x at some point a, b, my definition, maybe I should add my a, b here if I'm actually defining it, my partial derivative at a point. It's going to be equal to the limit as h approaches 0, looking familiar, right, of f of x plus h, we're evaluating it x equals a, sorry, a plus h, comma b, minus f of a, b, all divided by h. So a lot of similarities with our basic definition of a derivative. Notice that the h is only added to the x component because I'm only taking the partial derivative with respect to x. We have an exactly analogous definition for the partial derivative with respect to y. I'm not going to write out all those words. With respect to y. Partial derivative with respect to y. Our notation is very similar. I'm taking my partial derivative of my function ab with respect to y. That's equal to f sub y evaluated at the point ab. And again, it's the limit as h approaches 0 of f of a comma b plus h minus f of ab all divided by h. So these are our technical definitions. What does it mean graphically? This is where I think things get very interesting. So graphically, let's take some generic function that's a two-variable function. This is sort of my go-to picture for a generic two-variable function. I have my xy axis on the bottom, my z-axis up here. And I'm looking at what is my partial derivative at the point AB. So somewhere down here in the xy plane, I have some point AB. I'll label this point AB. So I'm going A in the x direction and B in the y direction. Let's start with the partial derivative with respect to x. Let's analyze what each of these pieces are talking about in this definition. So if I want to look at what is f of a plus h comma b, well, that's the point a plus h comma b is going to be down here in the xy plane. So if I'm taking a and I'm adding h to it, I get a new x-coordinate, a plus h, and the y-coordinate is still b. So this is my new point, a plus h comma b. And I'm evaluating these points up here at their functional values, because here f of a plus h comma b is going to be what happens when I take this point and see what happens when I plug it into the function. So here's my point. My output is going to be at a height of f of a plus h comma b. And my output of the point AB is going to be something like this, with a height of f of a comma b. So when I'm looking at this difference divided by my value h, really, I'm looking at a slope. It's just a very particular slope. It's the slope emanating from this f of a plus b, from this f of a comma b height. This is a point in three-dimensional space. And I'm looking at what is the slope as I travel along the arc where y is exactly equal to b. And the slope of this tangent line in the x direction is going to be exactly equal to my partial derivative with respect to x. I'm going to write that down. The slope of the tangent line in the x direction is exactly our partial derivative with respect to x. Similarly, if I wanted to draw this picture for my partial derivative with respect to y, which I'm going to do in red, I'm going to look at the difference. My x values will stay the same. My x values aren't changing at all. They stay at a. But my y values, I'm looking at the change from the point AB to the point a comma b plus h. So I'll erase this below it. My red point here is going to be the point a comma b plus h. And it maps to a point up here somewhere on this three-dimensional surface. And as my h gets smaller and smaller, the slopes of these secant lines are going to get closer and closer to the tangent value along some three-dimensional curve. It's like I took this two-variable function and I sliced it, leaving my x's exactly constant to a. So I'm only concerned about, as my y's change, how is the height of the function changing? So this is saying my y's are changing, and I want to know how much does that affect how much my z's are changing. Hopefully visually these make sense. Let's go ahead and compute some examples. So it's all well and fine to know the theory. It's really nice to be able to have a graphical interpretation of what's going on. Finally, algebraically, how do we actually compute partial derivatives? So let's say I have some function given by f of x is equal to, I guess it doesn't really matter. I'm going to do 3x squared, oh, sorry, let me back up. This function isn't going to be a function of just x. Let's say it's a function of not just x and y, but z as well. So I have a 3-variable function, a function f of x, y, and z. And let's say it's given by something like x squared e to the yz. So I have the 3 different inputs in our 3, and I have a single real-valued output. Visually, we can't really interpret what's going on, but we can still compute partial derivatives. So the first thing that I'm going to do, I want to compute my partial derivative with respect to x, which is also written f of x. What is this equal to? Well, I know that I'm taking the derivative with respect to x. My y's don't change, and my z's don't change. So I'm going to treat y and z as constants. And we know how to take derivatives when I have x squared times a constant. The constant is just going to be a coefficient that goes along for the ride when we take the derivative. The derivative of x squared is 2x. And this, we don't do anything with. We treat it as a constant. So nothing happens to that term. And this is our partial derivative with respect to x. Similarly, I could take my partial derivative with respect to y or with respect to z. And in this case, if I take my partial derivative with respect to y, I'm treating x as a constant, and I'm also treating z as a constant. In my head, I could be thinking to myself that this is like taking the derivative of something like 3e to the y times 2. Because I'm thinking of my x's as constants, and I'm thinking of my z's as constants. And how would I take the derivative of something like this? Well, a little thought bubble, because I'm thinking this to myself. The coefficient is just going to go along for the ride. So when I take my derivative, the coefficient will stay. And when I take the derivative of e to the y times 2, I'm going to need to use chain rule. The derivative of e to the stuff is just e to the stuff times the derivative of that inner function. And the derivative of 2y is 2. So this is my thought bubble to help guide me when I take the derivative of this somewhat complicated partial derivative. So let's look back at what I did. I'm treating x squared as a constant because I'm taking the derivative with respect to y. If x squared is a constant, I leave that out front as x squared. When I take the derivative of this term, I end up with e to the yz, because the derivative of e to the stuff is e to the stuff, times, by chain rule, the derivative of this yz part. The derivative of yz is going to be, thinking of z as just a coefficient, z. Notice how that lines up with this derivative that we were doing in our thought bubble. The coefficient that's x squared just goes along for the ride, and I multiply it by the z value, which was because of chain rule. A 2-variable example. So I think it's good to see a couple of examples of these. So let's say I have a 2-variable example. G of x, y is equal to the sine of xy plus x. So I take my partial derivative with respect to y. So dg dy, which is equal to g sub y. Again, I'm going to have to use chain rule. I'm thinking of x as constants, and y is the only thing that I'm thinking as a variable. So the derivative of sine is cosine of xy. And by chain rule, I need to multiply by the derivative of the inside. And the derivative of a constant times y is just going to be that constant, plus a derivative of constant. Because y is our only variable, we're treating x as a constant, the derivative of the constant is just 0. So I'm left with my partial derivative of g with respect to y is just going to be the cosine of xy multiplied by x.